This lesson is for day 6. We're going to be graphing a quadratic in vertex form. So we've already worked on putting it into vertex form yesterday with completing the square. Now I'm going to be asking you to graph using that form. So the first thing is we should be able to review this really quick, but the vertex here in this first problem should be 5, 2. And this is going to be a maximum because we know that this is going to open downward, so this parabola looks like this with the vertex being up at the top. So this has to be a maximum value. Now the only other one I think that I should probably do with you is problem 4. And in this case, you have this -6 that could be on the opposite side as y plus 6. So sometimes you might see that k value come to the other side. So in this case, the vertex would be -4, -6, because of course if it was on the other side it would be a positive 6. And this in this case would also be a maximum because that value, the a term here, is -9, so it opens downward. Alright, now when it's in vertex form, we can graph the vertex, and then we can graph using the idea of stretches and shrinks for additional points. So what I want to do in order for you to understand actually how to do problems like 1 and 2 here is to take you to the most basic graphs, y equals x squared. This is our mother function here. Okay, so let's say we started with our mother function y equals x squared. Now here's our table of values. And I'm just showing you these table of values here because I think it's important for you to understand that when you start at your vertex, 0, 0 is my vertex, and if I go left 1 and up 1, I arrive at this point, -1, 1. And using symmetry, I can also go right 1 and up 1, but I'm left with this point here, 1, 1. And if I move 2 to the right from this vertex, if I go 2 to the right and up 1, 2, 3, 4, I have the point 2, 4. And this other point is found by going left 2 and up 4. Okay, so left 2, up 4. So basically I want you to remember right 1, up 1. Okay, right 1, up 1, right 2, up 4. Those are your basic points, and then you can use the points of reflection also to get, left 1, up 1, and left 2, up 4. Now when you look at the graph of y equals 3x squared, this time look at all of the table values here. So it's really similar. It's obviously a stretch, right? This value here is a positive value. It's going to open up and it's going to be stretched. But if you look at those values, notice that they are 3 times as large as all of the y values here. Okay, if I multiply all of these y values by 3, I end up with these y values on the right-hand side. So look at your points also. When I went to the right one, instead of going just up 1, I went up 1, 2, 3. So I took that normal point, which I go up 1, and I multiplied it by a factor of 3 to stretch it to get up to this additional point. If I go left 1, I also have to go up 3 here. So left 1 and up 1, 2, 3 lands me here. From the vertex, if I want to plot that next point, instead of going to the right 2 and up 4, this time I go to the right 2 and up 12 units to get to this this point, 2, 12. Okay, so here I'm going right 2 and up 12 because I'm multiplying that value and stretching it. Instead of a factor of 4, it's now a factor of 12. Okay, so let's start to graph this first problem here. Okay, so those were some basic ones with the vertex at 0, 0. Now my vertex is going to switch, so I'm kind of using the idea of transformations here. This is going to shift the graph left 1 and to the left 7. So left 1 and down 7. Did I say left 1 and left 7? I meant left 1 and down 7. Places that vertex here at -1, -7. Okay, if we move that 7 to the other side, now it's a lot similar to the, it's way more similar to the absolute value functions that we worked on, where you subtract 7 here, so this would shift it down 7, right? I hope you remember that when it's on the inside it does the opposite, when it's on the outside you use the same sign, so it would shift it down 7. So anyhow, we're at this point. Now, without having to do a lot more work, I can get pretty much all the other answers here. The axis of symmetry is obviously x equals -1, so let's graph that. And now for additional points, I can use this concept that I'm stretching it by a factor of 3. When I start at that vertex, I can go to the right 1, and instead of going just up 1 and putting my point here, it's stretched a unit of 3 times. So it's 1, 2, 3, up 3 now. I can go left 1 and up 3, or just use vertex symmetry here. I can also go to the right 2 and up 12. So up 12 would give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would place me here at this point. Using reflection, I know the other point has to be here. Okay, so this is the graph. Now I have 5 points, and it's pretty basic and very easy when you have it in vertex form. Now the only things that we're missing here, if you look, my y-intercept is found really easily here. It's just at 0, -4. But my x-intercepts are not so nice. They don't go through the corner of any box. So I have to actually find the x-intercepts, which I think you're going to find very simple. Remember, an x-intercept is just when y is equal to 0. If I set y equal to 0 here in my original function, this term goes away, and I'm left with 7 equals 3 times x plus 1 squared. Now if I solve for x, I'm going to divide out the 3, and I'm going to take the square root of both sides. So I have positive or negative root 7/3 equals x plus 1. Subtract the 1, and now I have x equaling -1 plus or minus the square root of 7/3. So you have two coordinates here, -1 plus root 7/3, comma 0, and -1 minus square root of 7/3, comma 0. Now what you can do is put them in one point, so you don't have to rewrite that twice. You can just do -1 plus or minus the square root of 7/3, comma 0. Alright, that was the introduction to your very first problem. Now I would like you to try number 2 on your own. Notice that it is opening downward. When it opens downward, it doesn't affect how you graph those points. It's still going to move, one up 1 or down 1, and then, or left 1, right 1, sorry, and then you're going to move it down instead of going up. So I'll do one with you guys that does have a negative value. I'm going to let you guys do number 3 here on your own. I will work on 4 with you, okay, because this is going to be a shrink this time, which we haven't worked on yet, and it's also going to open down. So you can go back after you watch 4 and do 2 and 3. Alright, now in this problem, the vertex is at -2, 4. So I'm going to start at -2, 4, and I have an axis of symmetry at x equals -2. I know that this parabola is opening downward, and now I'm going to start graphing points. Now my first point, if I went to the left one and down 1, that would be the normal graph of just -x plus 2 squared. Okay, but now I have this 1/3 out in front. It's really difficult to try to figure out what 1/3 times this 1 is. I know it's only going to be 1/3 of the way that it's going up now. That's why this graph is going to end up widening out big time. Instead of being a stretch, we are shrinking the graph, making it fatter. But it's really tough to try to graph that first point, that integer value there. Likewise, if I try to go to the left 2 and up 4, 4 times -1/3 gives me a value of -4/3. Now I could graph that point and try to shrink that down by 1/3, but I don't want to do that either. I want to try to pick values that make me land right on the corner of a box. Okay, so make sure you stay with me on this one, because I think you might get a little confused if you don't pay attention to what I'm trying to say to you. So let's say that I were to expand my table of values and include the point 3, x equals 3. If x equals 3 in that normal graph, I'm doing the mother function here, y equals x squared, okay? If I plug in 3 here, I get 9. 9 is a number that's very easily divisible by 3 or multiplied by 1/3. So this time, from this graph, I want to go to the left 3 units and then down only 3, 1, 2, 3. Okay, I'm also going to move to the right 1, 2, 3 units and down 1, 2, 3. So that's how I can find some additional points here in a much easier way for me to do that. Now, other multiples of 3 that would result from here squaring an x value would be a number like 81. Now, this is the result of squaring the number 9. So like nothing in between here. 4 squared gives you 16. That's not divisible by 3. 5 squared is 25. 6 squared, oh shoot, I skipped 6 squared. Durr. So never mind. 36 is easily divisible by 3, right? 6 squared gives me 36. So now I can go left 6 units, so 1, 2, 3, 4, 5, 6. And instead of going down 36 units, I'm going to go down only 12, because 1/3 of 36 is 12. So I go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then I do the same thing. I can just use reflection though. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 places me right there. And that would be the graph here when I have a shrink. So shrinks I think are much more difficult to do, especially something like 1/3. Okay, now we need to find the y-intercept. The y-intercept here, it looks like it's going through 0, 2, but I don't want to make sure, I don't want to just guess and think that, oh yeah, it's going through 0, 2. So let's make sure that what the y-intercept is. We are going to plug in 0 into this function here, because x is equal to 0 for a y-intercept. So now I have y equals negative 1/3 times 0 plus 2 is just 2 squared plus 4. So I have negative 4/3 plus 4, and which is clearly not going to be 2, so that's why you don't want to just guess from your graph. And so my y value here is going to be 8/3. So I have the point 0, 8/3 for my y-intercept, and now when I find my x-intercept, I'm going to let y equal 0. So I have 0 equaling negative 1/3 times x plus 2 squared plus 4. And again, this is where you're going to just use the square root method because it's probably the quickest. So subtract the 4 over, and then you can multiply to get rid of that 1/3. Multiply by negative 3 on both sides, so you get 12 equals x plus 2 squared. Positive 12 equals x plus 2 squared. Now when you take the square root, you will have to reduce that radical. It's positive or negative root 12. And now I get positive or negative 2 root 3 equals x plus 2. Subtract the 2 over to the other side. So we have negative 2 plus or minus the square root of 2 root, plus or minus 2 root 3. So now I have the coordinate negative 2 plus or minus 2 root 3, comma 0. Alright? So that's the last graphing question I'm going to do with you. Please repeat something if it's not making sense. Go back, especially make sure you understand this whole idea of your original points here and how you can find additional points by just using that very simple concept of just translating, to the right one, up one, and so on. Okay, next up, we are going to write the equation of a parabola when we are just given a vertex and a point on the graph. Okay, so algebraically, what we know is if we have the vertex at 2, negative 1, then in our vertex form, which is y minus k equals a times x minus h squared, this is a form that we need to make sure we have memorized. We know that the vertex can be replaced in here for h and k. So I have y minus a negative 1, so y plus 1 is equal to a times x minus 2 squared. And now the only thing I have left to find is one variable, a, okay, in order to write out the equation of this parabola. Now, I am given an additional point here, 4, 3. This coordinate represents an x and a y. Always remember that every point is always an x, y. So what we can do is plug in the point 4, 3 in for x and y. So that means the y here is going to get replaced with a 3. The x is going to get replaced with a 4. This is similar to something we've already done with absolute value functions, but I want to make sure we understand how to do this. So we're going to do 3 plus 1 equals a times 4 minus 2 squared. So now all we have left to do is solve for this a. So I get 4 equals a times 2 squared, so 4, which means a is equal to 1. 4a equals 4 leaves you with a equals 1. That means that the original quadratic was y plus 1 equals 1 times x minus 2 squared. We don't really need that 1 out in front, but this would be with all those values, a, h, and k all replaced. So that's what we're looking to do here, is just solve it algebraically. I'm going to do one more with you guys and let you guys do number 3 on your own. Now in number 2, we're going to start with y minus 9 equals a times x plus 2 squared. Again, we're just taking this value here, this h and k, and plugging it into our vertex form. So now I'm going to solve for a by plugging in the point 3, 5. So I take the 5, I plug it in for the y, so I have 5 minus 9 equals a times, the 3 will replace this x, so 3 plus 2 squared. So I have negative 4 equals a times 5 squared. So I have negative 4 equals 25a. If I want to find a, I would divide by 25, so I'm left with a equaling negative 4 25ths. So my quadratic would be y minus 9 equals negative 4 25ths times x plus 2 squared. So please work on number 3 on your own and check with the key. Last up, it's really just the same type of problem that we just saw, but this time you're going to find the equation when you're just given a graph. So when you're given the graph, think about what you need in order to solve for vertex form. Well, first you need to know what the vertex is. Luckily for you, we have that here bolded. So my vertex is at 3, -4. And now my point, which I already have bolded as well. So you would have to normally select a point, but I'm picking the point for you. That point is 7, 1. So now this turns into the exact same questions that we had here, where I gave you the vertex and the point. Here you have to figure out what the vertex is and what the point is, and do the same process. So I'm going to start with y minus -4, so it'll be y plus 4 equaling a times x minus 3 squared. So I start with that vertex, and I plug in the h and the k values right into here. And make sure you always have this term squared. A lot of people forget this part, and then they end up with a crazy number that's way far off. So make sure you do plug that in correctly. It's the squared term here. And now I'm going to plug in 7, 1. So I have 1 plus 4 equals a times 7 minus 3 squared. If you don't square this number, you obviously just have 4a here instead of 16a. So we have 1 plus 4, 5 equals a times 4 squared is 16. So we have a equaling 5/16. So that quadratic is now y plus 4 equals 5/16 times x minus 3 squared. Please try number 2 also on your own. It'll just give you more practice, like that last question that I skipped. And you should come into class ready to work tomorrow. I'll see you tomorrow. Nice job.